In this video, we're going to talk about one-to-one functions and inverse functions. So the definition of a one-to-one function is all in its name. So it means that there's one distinct y or output for every x that you have. So if I was to look at a domain and range kind of graph like these two here, I have one distinct y for every single x that I have, so that's a one-to-one function. But here, this is not one-to-one because for -2 to 5, that's fine, and 13 to 18, that's fine. But 4 and 8 have the same output. So in order for that to be a one-to-one, 4 and 8 would have to have two different y's, or ranges that it would map to. So that's not one-to-one. So if I was to look at a graph of a function, so this is a cubic function, this is one-to-one because there is one x for every y. Nothing overlaps as far as a y concerned. And then for a quadratic, although it's a function, it's not one-to-one because for every x here, we don't have a distinct y. So when we talk about the graphs of one-to-one functions, there's a really easy test that we can perform, and that's the horizontal line test. Not to be confused with the vertical line test, which tells you if the graph is actually a function or not. But the horizontal line test tells you that a function is or is not one-to-one based on if you draw a bunch of horizontal lines. If it's one-to-one, it will intersect with the graph once or 0 times. If it intersects more than once, then it is not one-to-one. So for example, this function here is not one-to-one because right here and right here it intersects the same horizontal line, and then it happens a couple more times. So obviously it's not one-to-one. But this function here is one-to-one. I can draw an infinite amount of horizontal lines, and it will only intersect my function once. Now moving on to inverse functions, there's a couple of things we need to talk about. The first being the way that we represent the inverse function. Of f of x, we write it f to the -1 of x. So if you ever see this, whether it's g to the -1 of x or whatever it is, that just means that it's the inverse of g or f or whatever the letter happens to be. Also, the graph of f of x is reflected over the line y equals x. So I know that this looks really weird, but the f of x function is this red function here. And then if I flipped it over this dotted line, which is y equals x, it becomes the inverse function. So what happens when I flip the graph of f of x over the line y equals x to get the inverse function, the domain and range of the original and its inverse flip. So the domain of f of x is the range of its inverse, and vice versa. The range of f of x is the domain of its inverse, and you can kind of visualize it here. And so one last thing for now about inverse functions is that if the function f of x and g of x are in fact inverses of one another, then that means if I plug the function g of x into f, it will produce just x. And the opposite is true. If I plug f of x into the function g of x, the result will just be x. So let's see if that's correct. Let's find the inverse of 2x plus 3 algebraically. So the first thing that I do is I write f of x as y, because they mean the same thing, and then I write my 2x plus 3. So the first step here is to actually flip your x and your y, because remember, the x and the y values for the inverse flip, right, domain and range flip. So that means x and y flip. So that becomes x equals 2y plus 3. So now I'm going to solve in terms of y. So what I do here is I move over the 3, I divide it by 2, so I get the inverse of f of x to be x minus 3 over 2. So let's actually call this g of x so I can use my f of x and g of x rules, so the composite function, right, f of g and g of f, to prove that they will both equal x. So first I've defined f of x and g of x, right, so g of x is the inverse of f of x, and if they are inverses of one another, if I plug this into here or that into there, then they should both equal x. Let's see if that worked out. So I'm going to plug this function g of x in for this x right here in f of x, and I work it out, and it does equal x in the end. And so I'm going to flip that, and I'm going to take this whole function and plug it in for x right here, and that also works out to be just x. So I've done it correctly, and these two are inverses of one another. And I can also check it graphically. So the red function here is f of x, and the blue is g of x, and the green line is my y of x. So they literally flip over this green line here, y of x. So every point that is on the red line, so for example 0, 3, will become 3, 0 on the blue line. So now let's do one more algebraically that may not be as easy as the last one. So let's say that f of x is 2x plus 1 over x minus 1. So I set it up like the last one. I make f of x y, and I swap my y for x and my x's for y. And the trick here that I use is, because this is a fraction and it has two y's, which is not ideal, I put this x over 1 and I cross multiply. So I distribute my x to my y and my -1 to get xy minus x. I then bring over this 2y and move over this x, so I have my y's on one side, pull it out, divide by x minus 2, so I get the inverse of f of x is equal to x plus 1 over x minus 2, including x can't be 2. So I can also look at this graphically. So red is f of x, blue is the inverse of f of x, and green is my reflection line, y equals x. So this red curve becomes this blue curve flipped over this line, as well as this blue curve here becomes the red line, or this red curve over here. Kind of confusing to see, but they do flip over each other. And you can check to see whatever xy points on red become y comma x on the blue curve. And that's going to do it for this video. Thanks for watching.